All right, let's jump right into this explainer. Today, we're breaking down the critical sustainability metrics for the rapidly growing wind technology sector. Look, as wind turbines scale up to staggering new heights, the developers building these absolute giants are facing a really complex web of environmental, social, and logistical hurdles. To navigate all of this, the industry relies on a very specific set of accounting standards to measure and manage those risks. We're going to unpack exactly how these companies are held accountable.
Here's a quick look at our roadmap. We'll trace the life cycle of these projects across 6 core areas: the wind industry standard, onshore versus offshore challenges, workforce health and safety, ecological impacts, materials efficiency, and finally, tracking turbine backlogs.
Starting off with Section 1, the wind industry standard, and establishing the framework.
So, first things first, it's essential to understand the foundation here. This framework is managed by the International Sustainability Standards Board, or ISSB for short, and it becomes effective for annual periods beginning in 2025. Think of this as the definitive blueprint for how wind technology manufacturers and project developers actually have to report their sustainability risks. It ensures that when you or investors or local communities look at a developer's track record, you're seeing standardized apples-to-apples data.
And as you'll see, the standard doesn't just ask for vague, feel-good promises. It demands specific, rigorous metrics. Some of these are purely quantitative, like measuring physical weights in metric tons or noise in decibels, while others require some pretty in-depth discussion and analysis. It's a comprehensive look at the whole shebang, from worker safety rates all the way to the sheer efficiency of the materials being used.
Moving right along to Section 2. Onshore versus offshore challenges and the geographic divide. Now, what's really fascinating about this standard is how it distinguishes between the two primary environments where these turbines are actually built. The crucial point here is that whether you plop a turbine on land or out at sea creates massive differences in both its wind-generating capacity and its development hurdles. Offshore installations, well, they get to tap into stronger, far more consistent ocean winds. This allows for significantly higher generating capacities and dramatically larger turbines. I mean, some of these things are now standing taller than the Eiffel Tower. But the development challenges are monumental. You're dealing with deep water foundations, brutal marine weather, and insanely complex underwater cabling. Onshore installations, on the other hand, are often more accessible and cheaper to install, but they face their own intense geographic realities. Think land acquisition, proximity to local communities, and dealing with varying wind consistencies. The standards absolutely require companies to account for these very distinct geographic realities.
Okay, Section 3, Workforce Health and Safety, focusing on operations and maintenance.
Let's talk about the human element. Operations and maintenance, or O&M, is where things get very real. Maintaining these massive structures is inherently hazardous work, for sure. Technicians are dealing with extreme heights, incredibly heavy moving mechanical parts, and severe, high-voltage electrical hazards. An entity's safety record here is absolutely paramount. Because, accidents don't just cause operational downtime, they directly impact a company's reputation, they reduce demand, and they severely drive up wind farm insurance costs.
To quantify this safety record, developers have to report their TIRR. That stands for Total Recordable Incident Rate, alongside their fatality rates. And here is a critical detail, so pay attention to this. They must report this not just for their direct employees, but also for their contract workers. That's huge. Whether an individual is on the company payroll or hired through a temp agency, if they are supervised by the entity, their safety data has to be tracked. This basically prevents companies from outsourcing their most dangerous tasks just to hide their true safety record.
Which brings us to Section 4, Managing Ecological Impacts Across Land, Sea, and Sky.
Once a site is chosen and workers are safe, how do we actually measure the environmental footprint of building it? Here is where that onshore versus offshore distinction really rears its head again. Developers are navigating completely different ecological minefields depending on the geography. Offshore projects require careful monitoring to ensure underwater construction doesn't completely devastate fragile marine ecosystems. Conversely, onshore projects require massive land acquisitions that can drastically alter local habitats. But both environments present severe risks to local animal populations, some of which might even be endangered. If a developer ignores these concerns, they aren't just harming the environment. They face severe project delays, permit rejections, and intense community pushback.
To address these impacts head-on, manufacturers are investing heavily in some pretty innovative turbine designs and operational controls. They're deploying physical technologies like radar and ultrasonic transmitters to detect and deter birds and bats.
They're modifying turbines with blade heating elements for harsh climates. And crucially, they are using operational software that allows for sudden curtailment. That essentially means the turbines can rapidly slow down or stop spinning entirely when a flock of birds approaches, mitigating wildlife risks in real time. Pretty smart, right?
Additionally, one of the biggest hurdles for onshore development is community opposition, which very often stems from noise. The constant whoosh of massive blades can be pretty disruptive. Because of this, developers must meticulously track and report the average A-weighted sound power level of their delivered turbines. This is measured in decibels and categorized by their specific wind turbine class. It's just a vital metric for proving that a new wind farm isn't going to be a total nuisance to its neighbors.
Pivoting now to Section 5, Materials Sourcing and Efficiency. Basically, how we're building these giants. Modern wind technologies, especially those highly reliable direct-drive turbines, rely heavily on what are known as critical materials. We're talking about rare earth elements like neodymium and dysprosium, as well as minerals like tantalum and tungsten. These materials are absolutely essential for the turbines to function efficiently, but they are highly subject to supply restrictions. Deposits are often concentrated in just a handful of countries, which means the entire wind industry is vulnerable to geopolitical supply bottlenecks, not to mention intense competition from other tech sectors. So, to protect against wild price volatility and supply chain shocks, the standard mandates that companies disclose their specific strategies for managing these risks. This isn't just about noting the risk, it's about action. Companies have to show their homework. They must detail how they're diversifying their global suppliers, stockpiling critical materials, investing heavily in research to find alternative substitute materials, or even funding advanced recycling technologies to reclaim rare earth elements from old, decommissioned turbines.
But it's not just about what materials they use. It's about how efficiently they're using them. As turbines grow exponentially in size to capture more wind and improve energy output, the sheer weight of these structures skyrockets. Often, just the top head alone weighs hundreds of metric tons. Therefore, developers must report a very specific metric: the average top head mass, which includes the nacelle and the rotor, but excludes the blades, divided by the turbine's capacity. This basically gives us metric tons per megawatt.
And this capacity metric, it's everything. Turbine capacity, often called nameplate capacity, is the maximum megawatt output generation of that turbine. By tracking this megawatt capacity against the literal metric tons of steel, carbon fiber, copper, and fiberglass required to build the top head, investors can see exactly how efficiently these giants are being engineered. If a company can increase their megawatt capacity without drastically increasing their material weight, well, they've got a massive competitive advantage.
Finally, Section 6, Tracking Turbine Backlogs. Let's look at the financial impact.
All of this eventually trickles down to turbine order backlogs. Say a developer fails to properly manage visual aesthetics, or ignores land use concerns, or accidentally threatens local wildlife, it very often leads to projects being completely halted. Under this standard, companies must explicitly report the financial value of any canceled, deferred, or terminated turbine orders in their backlog that resulted directly from community opposition or ecological impacts. This literally puts a hard dollar amount on sustainability failures. You can't just brush a canceled permit under the rug anymore. If a community rejects your project because your turbines are too loud, that financial loss is right there on the balance sheet for everyone to see.
So, this leaves us with a pretty massive question to ponder as we wrap up this explainer. We know the demand for renewable energy is surging globally, but as developers push the absolute limits of engineering, building ever larger turbines to harvest maximum wind both onshore and offshore, how will the physical realities of the natural world and the very real concerns of local communities dictate their financial success? Will the backlogs of tomorrow's wind developers be driven by technological innovation, or will they be bottlenecked by ecological limits? It's a fascinating balancing act, and thankfully, because of these SASB standards, we now have the metrics to watch it all unfold.